Hello, everyone. Welcome to our webinar hosted by the Caltech Alumni Book Club. For the last few weeks, the book club has been reading Paper, Paging Through History by Mark Kurlansky. We asked Peter Sachs-Colopy from the Caltech archives to provide us some further insight into Paper. Peter Sachs-Colopy is a historian, archivist, and curator of science, technology, and media. As Caltech's university archivist, Peter leads a team that organizes and preserves the historical record of research at Caltech to facilitate understanding of the Institute's role in the history of science and technology. He recently curated the Caltech Archives exhibit, The Mind's Eye, Richard Feynman in World and Image. Peter also researches the history of the networks of people and institutions, from engineers to artists to psychotherapists, that emerged around the new technologies of portable video recording and video synthesis in the 1960s and early 1970s. We'll have some time for questions at the end. Now here's Peter to talk about Copernicus to Feynman, paper and print in the Caltech archives from 1500 to present.
Thank you. Good afternoon, everyone. Welcome to the Caltech Archives presentation this afternoon. I'm going to be talking about the history of the paper in our collections, which really makes up most of what we have in our collections here at the Caltech Archives. But I'm going to start with a slightly broader overview of what we are here. So you can see on this slide some of the range of Caltech's history, which we strive to document and to make available both to Caltech itself for institutional memory and to researchers of all sorts who are using this material for telling the stories of Caltech's history or other histories that touch upon us, or for reinterpreting scientific data from the past in order to support new theories and interpretations. So our collections that we use for this kind of work include the professional and personal papers of a couple hundred Caltech scientists and engineers. You can see here in the foreground the name of Richard Feynman on some of these boxes, and I'll come back to Feynman as one of the subjects of our collections later. Our collections also include other kinds of media, film, videotape, audio tape of Caltech events, of documentaries made about Caltech. You can see in the middle here my favorite format, half-inch open reel videotape, which is a format from the late 60s and early 70s, which we have several lectures recorded on. Our collections include scientific instruments and other apparatus from Caltech's history. So you can see here some electronic and electromagnetism apparatus, but we have devices from particle physics to Drosophila genetics, a variety of different fields represented there. Increasingly, our collections include digital media, often transferred between servers, but sometimes on tangible hard disks, floppy disks, etc., like you can see here. We also conduct oral histories with people who have stories to tell about their lives at Caltech, particularly faculty who have served long careers here. And you can find, again, about a couple hundred of our oral histories on the web. I would just recommend searching for Caltech oral histories, and you can learn a lot about the research, the life experiences, the collaborations between Caltech scientists. But I'm going to start our presentation today by talking about our rare book collection, because our rare book collection gives us the deepest view into the history of paper, of print, of binding, of both the materiality, the tangible form through which people exchange information on paper, and the content of the history of particularly physics and astronomy going back to the scientific revolution. The scientific revolution in the 1500s, 1600s was facilitated by print. It was this new technology that really made it possible for natural philosophers, as they were then called. The word scientist hadn't yet been coined. It was this new technology that made it possible for natural philosophers to exchange their ideas with their colleagues on scales that had never been done before, and for hundreds of people to read the same text at the same time and then debate it and build new ideas upon it. Much of this rare book collection that you see in this photograph, and this photograph I think is of about a fifth of our rare book collection, much of this collection was donated to Caltech by Ernest Watson, a physicist and dean of Caltech. You can see here his office in 114 East Bridge, which I believe is now a classroom. And I expect that you can tell from this photograph of his office that Ernest Watson was a very prolific collector of all sorts of objects, particularly artistic prints of early modern scientists and books, but you can see a variety of other things that he collected, many of which are now part of the Caltech archives in this photograph. And one of the things that Ernest Watson acquired in order to give to Caltech, one of the most exciting things and most rare things in our collection, is a copy of the first edition of Nicolaus Copernicus's On the Revolutions of the Heavenly Spheres, which was published in Nuremberg in 1543. So this is a book that is several hundred years old now. And it came to Caltech in 1955, so it's been here for some time at this point. And there are many things that we can say about this book. I'm going to start just by showing you a few different dimensions of it. So there it is sitting on a shelf, of course. Here's what it looks like when we look at the front. And once we open it up, we can see the title page, which explains to us that this is the book De Revolutionibus Orbium Celestium, so the revolutions of the celestial or heavenly spheres, as we tend to translate it into English. And this was the book that was sort of the most central to proposing heliocentrism as a way of thinking about what we now call the solar system, proposing that the sun is at the center of things and that we on Earth are not. And Copernicus did this in this work by explaining a system in the first part of his book, and then really devoting most of the book to showing how this system could be used predictably, how you could understand the positions of the planets as well as, or even better, with this system than with the competing geocentric systems that preceded it. So, as I've mentioned, this is a very rare book. The first edition in particular of Copernicus's work, there were only a small number of copies made, and a small number of those have survived over the hundreds of years to the present. But one of the things that's most special about having copies of these very old books is that each individual copy has had a unique history that's represented, for example, by the unique things people have written in it. So this copy lived almost all of its life in England. And we can tell that in part because people have written in it in the English language. So you can see on the title page towards the lower right corner, the top of the several things written in the lower right corner, someone has written to his loving friend, Mr. George Tomfer. So we don't know who Mr. George Tomfer was, but this certainly raises a question about the provenance, the history of the ownership of this book, and a potential for research there. Here that is a little closer, so you can make out some of the characters, slightly different spellings than we might use now, but there it is. People also apparently wrote inside of this book, although not in English, but in Latin, which the book itself is in Latin. So here's a passage very early in the book in which Copernicus is writing about his predecessor, his distant predecessor, Ptolemy, who he modeled much of his work on, and really part of the project of Copernicus was taking Ptolemy's sort of structure of understanding the world and the orbits of the planets and reframing it to put the sun at the center. And so here Copernicus is writing about Ptolemy's geography of the Earth. You can see words here like Egypt and Arabia. And someone has written in the margins something like Ptolemy was ignorant of some regions. So in a way, he's just sort of summarized, or someone here has summarized what Copernicus is saying and responded to it. But that practice of writing in margins, which many of us have in our books now, has existed as long as books have existed, and is an important part of how people interact with them. Another way that we can look at this particular book is in terms of the way that it was produced out of paper. And I'll get in a moment to the particular sort of paper that it was made out of. But a key thing about making books until the 19th century was folding paper in order to make a book. So some very large books, the printers would take a single sheet of paper and they would fold it in half. and that would be 4 pages that they could print on, a page on each side of each of those 2 leaves that they had folded. But smaller books would be made by more folding, as you can see in this illustration. And here I want to thank my colleague Elisa Piccio, who figured out sort of how we could show this to you using books from our own collections. So you can see that one of our larger books here is sitting on the bottom. This size of book is called a folio, and it just has paper folded once. And then a smaller book on top of it is called a quattro, because the paper is folded twice, but that makes 4 leaves, so quattro, 4. And then the one on top of that is an octavo, folded again to make 8 leaves. So the octavo uses a single sheet of paper very efficiently to get 16 pages, which would reduce the cost of a book dramatically, because the paper was quite a lot of the cost of a book 400, 500 years ago. You might notice here also that when you fold the pages in these ways, it creates these creases at the top, which would actually have to be cut by someone in order to actually read the book. But the printers didn't do that cutting. So if you bought a book, you'd sort of have to go through and cut each section in order to go through and read it. And in fact, many libraries that have books that are 400, 500 years old have some that are still uncut, that have never been read. The books in our collections have all been opened and read at some point or another, so we don't have anything like that to show you, but it's still sometimes the case. Turning back to our particular Copernicus, we can see a few other things by looking at the binding. So this is a leather binding. Someone who's more expert than I on these things has identified that it's an English leather binding. So again, reinforcing our understanding that this particular copy lived in one place for a very long time. And the binding is from the 1600s. So it's a bit newer than the book, which is from the 1500s, but not by a lot. It's been tooled. You can see the decorations. Those are called tooling. It gives us another way of seeing the sort of care that people went into taking care of this particular book, that its original binding may have worn out in its first 100 years or so of life, and someone went back and rebound it in another way. When one bought a book, and so we can look maybe inside of this book again, one bought only from the printer only what's called the text block, the part in the middle that actually has all of the text on it. They didn't buy the binding. And so someone would have bought this book and then taken it to a binder in order to have binding added, which then again probably happened 100 years later in its life as well. I'm going to be showing you several books from the first couple hundred years of printing, but I don't want to limit us to sort of books that were meant to be read cover to cover as a monographic complete work. Another very important early part of printing was periodicals, journals, and magazines. So this is a copy that we have of the 29th issue of the Philosophical Transactions of the Royal Society, which is often identified as the earliest scientific journal. This particular issue came out only 2 years after they started publishing the Philosophical Transactions. So it started in 1665. This is from late 1667. And the particular article with which this issue of the Philosophical Transactions opens is an article by Robert Hooke, who was curator of experiments of the Royal Society, who had a really crucial central role in particularly the English scientific communities of his time. And he is documenting the design of a micrometer, a very precise caliper, which could be used for measuring very small objects or for measuring larger objects with great precision. He describes it, as you can see on the first page at the bottom, as an instrument for dividing a foot into many thousand parts. And this is one of the earlier English texts that we have. I'll show you one still earlier in a moment. You can see that mostly the spelling of English from 1667 is familiar to us. The big difference that you might notice between spelling then and spelling now is that we write our S's differently. So even at the beginning of the table of contents, you can see the word description written with what looks like an F, but it isn't. It doesn't have a crossbar like an F would have. It's in fact sometimes called a scroll S. So you can read it as a description of an instrument for dividing a foot and so on. We'll see a few more of these archaic forms of English spelling as we look at a few more books. The other reason that I wanted to show you the Philosophical Transactions specifically is because that wonderful fold out with the illustration of the calipers, with the actually engraving that's been printed on here of the calipers, has this empty white space in the middle. And that allows us to take a very close look at some blank paper and to get some sense of what paper was like at this time. So paper in the early modern period, again in the 1500s, 1600s, 1700s, was generally not made of wood like it typically is now. It was generally made of reprocessed, recycled cotton rags. And so if you were to touch this material, you would feel a very different, thicker, rougher, more durable texture than the paper that we use in our everyday lives now. It's in fact a kind of cloth because it is made of cotton, and it has that sort of toughness to it. You can also see, looking up close at this particular piece of paper, and again I'll step back so you can see the context. You can probably see a sort of beige spot right in the middle of the philosophical transactions, and we're zooming in on that. You can see a grid pattern to the paper, and this grid pattern was imposed upon the paper when the paper was made by laying these little bits of little bits of cotton rag on a mold that would have looked something like this, a mold which had a frame with these vertical bars, and then it had horizontal wires that were sewn onto the frame. And so the horizontal wires leave very close together markings, and the vertical bars, which have a chain stitch on top of them, leave vertical markings that are about 1 inch apart. So we're looking at about 3.5 or 4 inches wide of paper in this particular image. So that very particular process of making paper is visible if we look closely enough at its product. There's a particular term for the very earliest books, for books printed in the 1400s. They're called incunables, which means from the cradle. Here at Caltech, we don't have any incunables. So I'm going to show you the next closest to the earliest books that we have, and they actually come very close. Although we don't have any books printed up through 1500, which would qualify as incunables, we do have books printed as early as 1502, so only 2 years off. The oldest book in our collection is probably this work of poetry, the green one here, by the Roman poet Horace. So our rare books are mostly physics, mathematics, astronomy, some chemistry, some biology, some geology, but we also have some more literary works, including this one. So Horace wrote in the BCs, the low BCs, but he wrote over 2,000 years ago. But once print came about, and once in the 1400s and 1500s, people were able to produce books on larger scales because you didn't have to have a scribe sitting down and writing out every word for every copy. Old texts like this were reproduced in larger quantities. And so this edition of Horace, again, is probably the oldest book in our collection. And it is actually a counterfeit, which someone has made sure to point out here in pencil, just to remind us that it is not a sort of genuine article of the edition that it says it is. So in 1501, there was an edition which was printed in Venice of Horace's work, and someone made copies of that edition that looked the same and claimed to be from 1501, but they did it in 1502, probably in Lyon in France. And you can see that this is somewhat rough printing. You can sort of see the edges of the individual letters of type, which isn't really maybe intended to be part of the print. Horace, of course, was writing in Latin, and this continued to be reprinted in Latin in 1502 when this was printed. At this point in time, it was expected that literate people would be able to read Latin. So it wasn't a language that everyone knew, but people who were reading books were likely to be reading books in it across Europe. And so it continued to be the main language of printing, and of course of many of the scientific works which we're looking at, including Copernicus. And this is actually quite a small book. It might be an octavo that was folded to make 8 leaves, but it might even be the next size smaller, a sextodecimo that had 16 leaves and 32 pages per sheet. It's a very small work. The earliest book that we have in English turns out to be really interesting, and I sort of figured out what it was specifically so I could show it to you, but then I discovered all sorts of fun things about it. So it's the Brown book here. It's an edition of Euclid's Elements which was initially written in Greek. So this is a translation that was made in 1570 into English, the first complete English translation of the Elements, and it was printed in London that year. It's a pretty large book. It's a folio. You can see it here sitting on the table, and I'll open it up and you can see the title page, which has this very intricate engraving representing the mathematical sciences. So you can see music, astronomy, geometry, arithmetic at the bottom. And then you can see some of the practitioners of the mathematical sciences, including the astronomer Ptolemy in the upper left. So there's this sort of representation of the world of mathematics in which Euclid exists. And again, you can see this sort of particular English spelling that includes those scroll S's, but that's mostly familiar to us. This edition of Euclid's Elements was made by a merchant who later became the Lord Mayor of London named Henry Billingsley. But it had an introduction by someone named John Dee, who was an advisor to Queen Elizabeth I, a mathematician and astronomer, and also an astrologer and an occultist. And at this time, these were often seen as all part of the sort of same activity. It was the search for deep truth in nature, which could take one to astronomy, or it could take one to attempting to understand nature as a realm of mystical secrets. And in this quite long introduction, John Dee describes all of the different sciences which one can do with mathematics. I was particularly struck on reading through some of this. And again, the spelling is sometimes a little peculiar to us now, but it's in English and you can take a look at some of it. I was really struck by the science of pneumatismy that he describes, which we might think from the name is the science of air, and it is, but it's actually the science of the geometry of the four elements, or at least he says here, water, air, smoke, and fire. Usually we would see earth instead of smoke when people in this period talk about the four elements. And a geometrical understanding of these, which one could develop through Euclid, is going to allow one to do all sorts of interesting things, including, you can see in the right margin here, to go to the bottom of the sea without danger. And he actually has some instructions on how you might use your expert mathematical knowledge of water to produce a submarine, which is a very simple submarine. If I'm reading it correctly, it's basically just an upside down cauldron. And the idea is that if you get inside of an upside down cauldron, you'll be able to force your cauldron down into the water and without harm descend to the sea bottom. I don't know if this was tried experimentally. One can certainly imagine some challenges involving buoyancy, but there's this great ambition for what one can do with the mathematical sciences in this period. And so even if this particular attempt might seem doomed to failure to us now, we can imagine that with some adjustments, this might be a start for building a proper submarine. And in fact, John Dee lays out the whole scheme of the relationships between all of the mathematical sciences as a sort of family tree. And this is, again, something that you see quite a lot in early modern texts, people trying to figure out how all of knowledge fits together into a coherent whole. But of course, the bulk of this book is Euclid's Elements. And so it starts with the definition of a point. It starts with some sort of straightforward foundational geometry, and has a number of diagrams, for instance, of how to draw an equilateral triangle using intersecting circles, which if you've studied geometry, you may be familiar with some of Euclid's proofs. In the later parts of the book, Euclid starts to demonstrate some geometrical facts about three-dimensional shapes. And the printers of this book made the really interesting decision to make the book itself three-dimensional, so that there are components of the book which one can fold out in order to visually demonstrate the geometry of three dimensions. So here, Euclid is describing a line which is perpendicular to a plane, and they have created a fold-out perpendicular shape. Here, Euclid is describing the shape of a prism, and you can see there's various drawings of a prism, but there's also these fold-out components which enable the reader of the book to create their own folded paper prism inside the book itself. It doesn't stay together on its own, so you can see I have my hand here holding it as I took the picture. So there's an incredible range in this work of Euclid, and an incredible sort of range of techniques used by the printers in order to provide us with as thorough an experience of the geometry as they could in the form of a book, really demonstrating the truth of Euclid's claims. We have some other copies of Euclid from actually around the same time, just 5 years earlier, 1565. I think in this case in Latin rather than in English, which I want to show you simply because their binding material is so different. These are bound in vellum, so they're in an animal skin. It might be goat, it might be sheep. It's actually a very difficult question to answer what kind of skin something is bound in. The main way to do that would be some form of genetic testing of the material. But we can see that that's quite different from a leather bound book like some of the ones that we've just looked at. And this is also a case where we have two copies of the same printing of the same work, although you can see that one had readers who were much more active with their pens than the other. I want to turn now to some of the other most prominent books in our early modern collection, and I'll use them to show you a few more interesting things about books themselves and about the physics and astronomy which they documented. So in 1955, Caltech bought from an Italian collector 202 really sort of crucial early modern works in physics and astronomy primarily. This Italian collector was named Prince Giampaolo Rocco di Torre Padua, and he had produced this really impressive collection of early modern books that were in very good condition that he had bought from a number of dealers, had rebound in a sort of uniform style to put his own stamp on them. So the bindings that you're going to see on the next several books are all bindings from the 1940s and 1950s. These are not terribly antique bindings themselves. But Caltech was able to acquire this whole collection using money donated by a trustee and Caltech associate named Harry Bauer. And this was all arranged, unsurprisingly, by Ernest Watson, the same physicist and dean who collected so much of our book collection. So here's again one example of these with Rocco's crest on the binding. This particular book is Johannes Kepler's Mysterium Cosmographicum. You can see it actually has an extremely long title, but the part of the title that historians and astronomers tend to remember is the Mysterium Cosmographicum part there. The cosmic mysteries. This is a small octavo book printed in 1596, and it's been referred to by one historian of astronomy as the first irredeemably sun-centered book. So when people read Copernicus, many people interpreted Copernicus as providing useful tools for calculating the orbits of the planets, but some people didn't think that he was actually saying that in reality the sun is at the center of the system. They thought that that was just a useful assumption for calculating. Kepler didn't leave that kind of room for interpretation. He was really clear that he believed that the sun was at the center of things. And he was also really clear on a lot of scientific positions that might seem to us now much stranger and more eccentric. So for example, Kepler saw in the proportions of the planetary orbits the same proportions as if you nest the Platonic solids, as he illustrates here. And he believed that this was a deep cosmic significance, which is not something that shows up in contemporary astronomy. Like I mentioned, I'll mention now that this is one of several books under which Kepler rolled out his sort of unique interpretation of the astronomy of the solar system. The next to have a similarly sort of massive impact was one, again, we have our Rocco binding here, called The New Astronomy. And The New Astronomy is largely an attempt to understand in immense detail the orbit of Mars, which Kepler studied very closely. And particularly this puzzle of the orbit of Mars, that if you observe it from the Earth, it progresses across the sky and then goes backwards, and then progresses again and then goes backwards, as is illustrated in this diagram. And this is actually one of the central problems of many of these astronomers in the ancient period, as well as in the early modern period of Copernicus and Kepler. And Kepler actually lays out some of the different ways that his contemporaries have dealt with this: Copernicus, Ptolemy, ancient so much earlier, and Tycho Brahe, who was actually a collaborator of Kepler. And he comes up with his own method that involves what we now know as Kepler's laws of planetary motion. So the idea that orbits are ellipses with the sun at one focus, that they sweep out equal areas in equal times. These are all ideas presented in this work, mostly through the detailed mathematical working out of the orbit of Mars. Kepler added another element to this interpretation in his Harmonici Mundi, the harmonies of the spheres, which is a work that does all kinds of interesting things. And this is actually maybe my favorite book in our rare book collection because of how much Kepler tries to do in one work. You can see in his table of contents here that he's going to deal with geometry, architecture, harmonics, metaphysics, psychology, astrology, astronomy, metaphysics again, right? Just if you look at the capitalized words. So there's this incredible range. And a lot of what Kepler's interested in is, again, things that seem a little bit outside the realm of modern astronomy. So he's interested in three-dimensional shapes. He's interested in the relationship between those shapes and the four elements. So you can see on the right in the middle, air, fire, quintessence, earth, and water. So the four elements plus one, which the world could be made up of. And the big contribution of this work of Kepler's that we still remember and still use is the idea that the periods of orbits are related to the distance of planets from the sun. So this is a useful sort of astronomical conclusion. But Kepler gets there again through methods that are really different from those of modern science. In particular, he sees music as one of the main tools for understanding planetary orbits. So here you can see each of the planets notated as a musical scale. And Venus has an orbit that is almost circular, so it has a constant pitch, whereas Mercury has a more eccentric orbit. And as a result, Mercury speeds up and slows down as it circles the sun. And so it has this sort of range of pitches that the frequency of the note represents the speed of the planet as it circles the sun. So there's this sort of way of using music, again, in a notation that still looks familiar to us, but to represent a relationship that we would probably represent in a very different way. Alongside our wonderful collection of Kepler works, we have the major works of Galileo, which was a real priority of Prince Rocco. So we have, for example, Galileo's work, the Sidereus Nuncius, usually translated as Starry Messenger, which was documentation of the incredible observations that Galileo had made with an early telescope. And Galileo basically breaks this book into two parts. The first part is about the Earth's moon, and Galileo himself painted watercolors and then made engravings based on those watercolors, which were printed into the book. The striking thing here is how little these moon diagram or moon drawings look like what we might see if we looked at the moon through a telescope. And there's been some debate about whether Galileo was simply a poor observer or whether his emphasis was more on communicating the imperfectness of the moon in order to make the point that not just the Earth, but other objects in space had been subject to change over time and to geological forces and to craters and so on. So the precise shapes were not so much the point. The other half of the Starry Messenger is about the moons of Jupiter, which Galileo illustrates in this very simple typographic form showing orbiting Jupiter in order to, again, communicate that there's more going on in the solar system than simply planets orbiting the sun or the Earth, depending on who you believe, but that in fact there are other objects orbiting those planets themselves. This is another copy of Galileo's Sidereus Nuncius. That first copy was the official printing that Galileo authorized. This is an unauthorized sort of pirate edition, and you can see someone redid the engravings in order to produce this pirate edition. They didn't have quite the detailed touch that Galileo himself did. This is also a smaller book, so it was designed to be cheaper and generally sort of produced more roughly than the official edition. Copyright law didn't exist yet, though, so Galileo probably didn't have a lot of recourse against that kind of piracy. And then another major work that I want to make sure I get a chance to show you from our collections is the work of Isaac Newton. One of the works that we, of course, remember Newton for is the Principia Mathematica, which is another of these sort of wide-ranging books. So Newton develops in this book a version of what we now call calculus, but he develops it in part in the process of trying to figure out mathematical principles that underlie Kepler's laws of planetary motion. So this is just at the very beginning of the book. He's developing a geometrical form of calculus, beginning with Kepler's second law that orbits sweep out equal areas in equal times. And Kepler had demonstrated this empirically. Newton is trying to figure out what the underlying mathematics is to that, and achieving quite remarkable things in the process. We also have a first edition, so the original form of Newton's optics, which is really wonderful in part for us because it is a work that Newton wrote in English rather than Latin. He sort of wrote in either language as it suited him. And it was then translated to Latin, so it was available in both languages. But this is sort of the original form of Newton's optics. And I picked these pages to show you because I found them really charming in that this is a report of an experiment that Newton did in which he made soap bubbles. And so it's the kind of experiment that you might imagine children doing in the backyard now, but with the sort of precision of scientific observation that Newton brought to it as well. Like many of the books in the collection, Newton's book includes engravings that illustrate some of its arguments. So here's some study of the refraction of light as it goes through a prism and the production of colors as a result of that. And finally, I want to show you one book that's much more recent. This is a first edition of The Origin of Species. So this is 1859. So we've actually skipped 150 years from Newton to Darwin. And during this 150 years from 1704 to 1859, printing and paper changed almost totally. So where Newton's work was printed on cotton rag paper with a hand press, so the type was set by hand. Well, Darwin's work, the type still would have been set by hand, but the press wouldn't have been operated manually by pressing down. It would have been operated with a steam pump that would have allowed the production of books at a much more rapid pace. Additionally, while all the books that we've looked at up to now came without their covers, and then the owner would take them to a binder and have whatever cover they liked attached, this is a work that came with the cover. So this cover is the standard cover for a first edition of The Origin of Species. It is itself made of cloth, so again, a very different material from the leather or paper or animal skin that we've seen on earlier books. And as a result of all of these changes, and particularly the change in paper material, it's now paper made from wood pulp as opposed to cotton. This is actually a much more fragile book, even though it's much less old. The paper is a little bit brittle. It's a very different sort of feel to handle it. This book also has a sort of fold-out illustration, but you can see I was being very careful in showing that to you because it's a book that one needs to be careful with. There's a variety of sort of threats to the durability of our collections. So for example, when this collection moved from Millikan Library to our current location in the Beckman Institute in 1992, my predecessors found insect damage to a number of the books. And they brought in an entomologist who found that most of that insect damage was from long ago, and we didn't have to really worry about it ongoing, but some of it was recent. So they took the books that had recently been exposed to insects and they collaborated with a research engineer for condensed matter physics here on campus, Niels Asplund, who took those books and put them in a glove box, pumped out the air, and pumped in nitrogen in order to kill the beetles that were eating a small handful of the books in our collection, which seems to have been a successful intervention, and we don't seem to have continuing trouble with those books. Books, of course, are made of organic materials, so they're very durable, but they do deteriorate over time. Bugs aren't the only thing that can deteriorate books. Heat can cause problems as well. A cool temperature basically will slow down all the chemical processes in the book, and so it will slow down its aging. We are also concerned about the humidity to which our books are exposed, trying to keep that moderate and stable. We pay attention to the light levels to which anything in our collection is exposed, because light as another form of energy can also damage paper. So I'm going to turn now, just to wrap up, from books in our collections which cover this many hundreds of years of the history of science, to our manuscripts, our papers, which cover a much more recent period of the history of science, mostly the period of the history of Caltech itself, from 1891 to the present. And in particular, I'm going to turn to this example of the Richard Feynman papers that you see here, sitting on our shelves, ready to be pulled out in order to answer research questions about the life and research of Feynman, about his relationships with his colleagues, about his process of working through the problems of the physics that he eventually communicated to others. And I've just pulled the first of this is, I think, about 120 boxes here on the shelf. They're each 4 inches wide. I've just pulled out the first one to show you. So you can see when I open it up that we have a number of folders there, each containing papers. In this case, this is letters between Feynman and his colleagues. And in addition to sort of organizing papers for researchers to come and use, we produce what are called finding aids, which are guides that include inventories of particular collections. So in this box, you can see, and this is just on the web, you're welcome to find it and to read it more fully yourself, but you can see that this box includes, for instance, communication with the Caltech biologist George Beadle and a number of other names that you may recognize. I pulled out the folder of correspondence with Enrico Fermi here, and we can see that there are letters between Feynman and Fermi. In this case, they're talking about whether their interpretation of a particular problem is consistent with each other or whether they disagree. So someone could take the time to sort of read through the whole correspondence, figure out exactly what's going on there, contextualize it, and say something new about it. As Elizabeth mentioned in my introduction, we currently have an exhibit here at the Caltech Archives that presents some of Feynman's work. So we've been able to exhibit, for example, some of the very first Feynman diagrams, pages like this one here, which are on modern paper made from wood pulp, which has held up pretty well in the years since. We've also been able to exhibit some of the notes that Feynman took as he was developing his Feynman lectures on physics between 1961 and 63. So these are notes, for example, for a lecture on curved space, which Feynman took on a placemat. Many of his notes are on paper that was not really intended to be used for doing science on, but had some other purpose. And these are maybe a bit more vulnerable because placemats are hardly made to hold up. Most modern paper has a certain level of acidity to it, which is sometimes referred to as inherent vice. It has a sort of ability to destroy itself over time. And so we're able to mitigate that to some extent by storing our acidic papers in materials that themselves are a little bit basic, that can maybe leach out a little bit of the acidity. So our folders and our boxes are called buffered, which just means that they're mildly basic. Another collection that I've been working with recently, and we'll get to your questions very soon, is the papers of the astrophysicist George Ellery Hale, who was a crucial member of Caltech's board in its transition to being a scientific research institution in the 19-teens and 20s, but also was the founder of Mount Wilson Observatory outside of Pasadena. So we have, for example, letters to George Ellery Hale from Albert Einstein in this case. We have plans which Hale was involved in for the design of the campus, which is now Caltech. Before, in 1920, we adopted the name Caltech. So the heading here is Troop College of Technology. And I'm going to end on what I find a particularly beautiful piece of stationery. And so that's why I've picked it. So this is a letter to Hale from the inventor Nikola Tesla, who was working on techniques for distributing electricity through the air, and had built this laboratory on Long Island with a really sort of bizarre and wonderful Tesla coil, which he included as part of his letters, as his letterhead. So the papers in our collections can show us all sorts of dimensions of the lives and research of the scientists and the engineers who have made the history in which we now live. And we welcome further participation with them beyond this seminar today. In particular, on seminar day, on Saturday, May 18th, we're going to have an open house here in the Caltech archives from 12:30 to 2, and we welcome any of you to join us. And we also have our exhibit on Feynman, The Mind's Eye, which is open weekdays from 11 to 4 through June 14th. And on seminar day, it will be open special in the late afternoon. So please, if you're here on campus, be sure to visit us then as well. Thank you very much. And now I'll be happy to chat with you a bit and answer any questions you might have.
Thank you so much, Peter. One question that I think is very relevant and just kind of more broad is when conservation or restoration is needed, who does that for you, or what might be the process for that?
Absolutely. We're a very small shop here in the Caltech archives, and so if you go to larger institutions, they may have staff who are conservationists who have that expertise. We certainly look beyond ourselves for that assistance. So in the past, we've had several books in our collections have binding repairs and other kinds of conservation action. We've worked with conservators at the Huntington Library, who have been able to assist us in some cases. They've had some changes in policies, so we might go to others in the future. But that's been a key part of our book preservation in the past. As far as other kinds of papers, we seldom are in a position where we need to worry about sort of repairing damaged things. Mostly what we do is we keep things in the condition that they're in for as long as we can, and hopefully we will preserve them for hundreds of years to come. So, for example, this paper, like I mentioned, it probably has some level of acidity in the paper itself, but if we store it at a relatively low temperature in relatively stable humidity and store it in those buffered materials, we don't really have to go in and repair the paper. We just maintain it over time. So the other thing that I would point anyone who's themselves interested in having conservation assistance with something that they own, if you're a collector yourself, is that there is an association of conservators, and I can find the exact name. It's something along the lines of American Society of Conservators, but I can find you the exact name, which maintains a really wonderful database of conservators. And you can look up conservators who specifically work with painting, who specifically work with book bindings, etc., in order to get assistance. So our next step with some of the items that we have that are in trouble now is asking around in the community of other archives and rare book libraries for who people have worked with who did a good job, and also looking in databases like that in order to find people to work with.
And what part of the collection, or how much of it would you say has been scanned and is available online?
Absolutely, thank you. I'll give two different answers regarding the books and papers again. So our rare book collection, we haven't really made a large scale effort to digitize, although there are particular pages from particular rare books that you can find in our image archive. And I would just maybe start by Googling Caltech Image Archive. You can find some of the really wonderful prints from books. There are other special collections libraries that have made really large-scale efforts, particularly at much larger institutions, to digitize rare books. And so Google Books, but particularly HathiTrust, HathiTrust, have really wonderful collections of early modern books where you can find other copies of many of the same books that we have in our collection. And those are great places to start looking at old books. As far as papers, there are some collections where we've done really thorough digitization projects. So the George Ellery Hale papers that I just showed you a few pages from, we've been able to digitize essentially in full. That's on the web at hale.archives.caltech.edu. And we digitized those from microfilm because they had actually been microfilmed already in the 1960s. So it doesn't have quite the aesthetic completion that me showing you these materials firsthand has. Sorry, I'm out of order here. To go back to Hale, for example, this page really did not come out well in the microfilm. The the letterhead at the top is sort of all muddled. But if you want to read materials in the Hale papers, you can read all of them online. We've also been able to do large-scale digitizations with a couple of important alumni collections, the Paul Maccready papers, the papers of a pioneer of particularly human-powered flight, but also a number of other areas of aeronautical engineering, and the Donald Glaser papers, Nobel laureate, particle physicist turned later biologist and neuroscientist. So we've been able to put really extensive portions of those collections online, really pretty much all of them, and you can find those through our website or through Google. In general, digitization is something that is probably not going to be comprehensive here or at other archives. I heard an estimate the other day that digitizing everything that archives have in paper is going to take about 1,000 years if we sort of keep it up for that long. And I think that we're going to be fine with sort of incomplete digitization, because while we have all kinds of things in our collections that we think are of wide interest, like this letter from Tesla to Hale, where I think that there are many people who are enthusiasts of one or the other of them who would love to see it, most of the stuff in our collections is something that occasionally a scientist or a historian is going to find useful, but it doesn't sort of, it doesn't attract the frequent attention that would really make digitization valuable. So our goal is to digitize the things that have the widest interest and to publicize and make it easy to visit us to see the vast volumes of things that might be of much more niche interest.
Is there a special setup to protect the collection from disasters such as fire in particular?
Yes, thank you. So, so we have our facility opened in 1990, and we have a wonderful state-of-the-art 1990 fire suppression system, which in many ways is better than if we built one now, because it uses a chemical called halon, which is which was then soon after it was installed found to damage the ozone layer, and so they stopped manufacturing it in 1994. So if we have a fire in the archives itself, we will have that halon fire suppression, which will push oxygen out of the space, extinguishing the fire. It would also, of course, extinguish anyone who was in the space, so evacuation becomes really critical in that kind of situation. But so we have really fantastic fire suppression here. The other piece of any kind of concern about fire with rare books, archives, etc., anything made of paper, the other concern is that the fire suppression itself often involves large quantities of water, and then you have wet materials. We don't have to worry quite as much about that because, again, our system doesn't use water. But even in those cases where fire suppression ends up soaking things, just in the last 20 or 30 years, there's been a tremendous amount of development in effectively drying and restoring wet papers, particularly through vacuum freeze drying. So if our materials do somehow get wet, we sort of have a plan that we'll be able to pack them out and get them into one of these big vacuum freeze drying units that will remove all of that excess humidity. And basically, it's never perfect, but basically archives that have been through that have been able to continue to operate with the same materials that they had before.
With the limited amount of space on campus, why do you think it's important that the archives have these books from as far back as the 1500s?
Yeah. So the space question is interesting, and it's more of an issue for us with the manuscripts, with the scientists and engineers papers, which really do take up a lot of space. The rare books don't take up that much space. So maybe I can start by saying that I think it's not as big an issue as with our manuscripts, where space can be a concern. The sort of most crucial use of these materials is for teaching. We have a course visiting us next term that is a course that has both sort of historical and contemporary components. It's about maps and geography. It's being co-taught by one of our history faculty here at Caltech and by a GIS engineer who works with the Jet Propulsion Laboratory. And they're going to be using a number of the books in our collection to show students the history of maps in a sort of firsthand way that they can see what maps felt like to handle, what maps looked like in terms of size and so on. All of the dimensions of handling the physical paper object that you wouldn't get if you looked at a photograph of it on the web. So that's really, for me, the most crucial application, is that it enables kinds of teaching that we wouldn't be able to do otherwise. It's also a research collection. So we do have historians of science and others. Some of the materials that I've shown you, physicists and astronomers have also looked at in order to understand the origins of particular ideas. And we want to get as much use out of it as we can as a research collection. We do have the sort of competition that the Huntington Library is right down the road, and they also have fantastic rare book collections in early modern science. We're always proud when we have something they don't, like the Copernicus that I showed you is something that's not in their collections. So there are these both teaching and research applications, the same as there are for other kinds of resources on campus.
And one more, because you were talking about seminar day, is the rare book collection available for alumni to look at, not only during seminar day, but maybe if they were visiting campus on another day, could they contact the archives to come and see those books?
Absolutely. So we are sort of core users are anybody who can articulate to us that they're doing some kind of research that would involve our collections. That doesn't have to be formal academic historical research for publication. It could be, I'm trying to understand better, the relationship between Kepler and Tycho Brahe, and maybe that's just a sort of hobby project, or it's related to what else you do in your life. But anything you can articulate as research will get our attention, and we'll give you as much help as we can. But we certainly welcome curiosity of any sort. And so, yeah, you're welcome to get in touch with us if you're interested in having a chance to look firsthand at some of what we've shown you. The other thing that, of course, is really missing from doing this over the web is giving you the chance to touch any of the books that we discussed. And as I mentioned, there is a real tactile difference in early modern paper than in what we're used to working with today. And I'd like you to have that experience. So please do get in touch with us if you're able to visit.
Well, thank you so much, Peter. It was really fascinating, and I think you're right. The only thing missing is that tactile functionality, but I think you did a great job of demonstrating like the 3D pictures that were in one of those books and everything. So I just wanted to say thank you on behalf of myself and the Caltech Alumni Association for this.
Absolutely, and thank you, Elizabeth, and the Caltech Alumni Association for this opportunity. And I hope everyone has enjoyed it. Please feel free to get in touch with any additional questions. You can email us sort of collectively at archives@caltech.edu, or I am pcolopy@caltech.edu. I'm happy to discuss further.
Thank you so much, and have a great day.